Okay, so you're being recorded from now on. Okay, may I just quickly do a little bit of ring call? So Jocelyn Cohen? Not here? Jocelyn? No. Oh, that's Lucy. Okay. Gail Denenbaum. All right. Hi. Yes, this is. Yeah. Eden, I've seen. Yes. Abigail Goldberg. Oh, hi. Hi. Evie Gutloff. Hello. Elena Hickton. Okay. Marcella Hamzani. Oh, hi. Shana, I've seen. Hi. Amira Eisenberg. Hello. Hannah Pupka. Hi. And Lizzie Zucker. Hi. All right. Good. Okay, so now we have the formalities. Okay, so I just wanted to, oh, hi, Jocelyn. Oh, there you are. Oh, hi. And Amira, where's you? Okay, revise that. It's more often, I would appreciate just give me a quick shout out if you're doing remote only. Just oh yeah. Hi. Sure. Yeah. There she is. Okay, good. Okay, so we're back to in-person lectures, and this will stay like this for the rest of the semester. So I'm back, and now we can really focus on also the troubleshooting to do that in person after class or before class. Or we can schedule in-person troubleshoot with R and or decoding. We can do remote session as well. If you want one-on-ones, just let me know, and then we schedule something and we'll make sure that everything works. I just want to quickly, so the quizzes were over pretty good, so I'm very happy with that. So the practice quizzes help, right? So that's, I think that's a good way to practice things and to get kind of comfortable with the concepts. Particularly, so there will be a couple of concepts involved, particularly today, for example, is a pure concept session, essentially. So there's no arithmetics and mathematics and statistics today. It's pretty much just about concepts. And I just wanted to quickly go through these points here. Practice lab 1. Everybody is kind of comfortable with that. I didn't have time to review it. Oh no, hands are going up for it. Yes. Yes. Yeah, there was a little bit of a problem from my end. It was my fault in the whole traveling madness. I kind of forgot to send out the code. I didn't attach it to the announcement. So please go through the announcement as I have posted it. In case you took the initial one, take the one that I posted. As said, these are low-hanging fruits. It's not about the code. It's not about finalizing it. It's not about learning the program. I want you to have those codes, and I want you to have run it once and understood it. So please rerun it in case you have not posted the one with the actual steps to solve the problem or to answer the question. So just rerun the one I posted lately. So I just really want you to have the code at your disposition, that in case you need it down the road, you will have a chance to use it. So that was practice lab 1. So how was homework 1? How is that going? Via Canvas. You can answer it in Excel. It's just important that you have answered it. And so just make sure that you point by point answer all the questions. You can do it in a Word document. That would be the nicest form. So you give me, but I need to see the calculations. And that's part of the whole assignment, is to essentially see that you have done the calculations the way we have done it in class. So both combined would be the most preferable kind of way, but it's fine if you just write it in an Excel, point by point by point, and you respond to all the questions, that's fine too. But either way. Important are the calculations. So I cannot create without the calculations. That was, so you can confirm it with the Excel functions, but don't rely on the Excel functions only. I really want to see that you have done the calculations.
Also, another question.
Mm-hmm.
You taught us like a step-by-step way to find standard deviation.
Yep.
But if we just like add Google it, then easier way at that time.
Well, there's the Excel function. That's exactly what I'm referring to. I want you to do the calculations in Excel. So step by step by step. So it's also when you do the standard deviation function in Excel, you need to know which one to pick, because the regular one, the STDEF in Excel actually doesn't give you the same standard deviation that we have calculated, because it's assuming a t-distribution. And as such, it's using the degrees of freedom instead of the sample size as we have done it. So we want the population level kind of standard deviation. It's a subtlety which you will understand in like half a month from now. And so we will talk about the t-distribution after the midterms. Good. What else? So today we talk about sampling and probability. We will talk on Wednesday about the normal curve, standardizations, and z-scores. This is usually when, I don't know who of you has done some stats to some extent. This is when things get a little bit accelerated. So it's getting a little bit more, I wouldn't say challenging, but it's more stimulating. Let's put it that way, intellectually stimulating. From there, we come to hypothesis testing. We will be talking about hypothesis testing already today a bit, the concept of hypothesis testing, and then we'll slowly transition over the confidence intervals, effect sizes, and statistical power. And this is also quite stimulating on an intellectual level. On the 1st of November, we're going to have a little review session. So please prepare for that review session, prepare questions. Bombard me with questions, please. That's what literally this session is for. Do the practice quizzes. Make sure you kind of have a good handle on the practice quizzes. Midterms will be those practice quizzes. It will be in person in the classroom, but it will be online on Canvas. But it will be an in-person kind of situation. Good. After that, we do a lab day. The lab day we can also use to kind of clarify questions you may have. And then we're going to start over on the 10th of November with the t-distribution. That's when it's going to get fun. That is really fun. You'll see. Good. Any questions to syllabus, homeworks, midterms, whatsoever? No? All right. Great. Good. Then let's get started. And I want to start today's lecture with, so this book, actually, if somebody looks for a good book, this is actually a fabulous book. It's a book solely about probabilities. And Leonardo Morodinov is actually a mathematician from Berkeley, I believe. And he wrote The Small Journey Through Time together with Stephen Hawking. And it's actually, this book is from him solely. It's just about probability. And probability is actually considerably hard to achieve. There's actually not much randomness in our lives. And so the only thing that is really random is the drunkard's walk. The walk of a drunk person on the street is not predictable. And this is kind of the funny thing why he chose this title for his book. And I like this example to kind of emphasize that it's actually considerably hard to achieve randomness. And when it comes to sampling and probabilities, randomness is actually not necessarily easy to achieve. And it's unfortunately for many occurrences in research, it's quite important to achieve something that is close to randomness, but it's problematic, which you will see after this lecture. So example I chose here to show you is when Apple developed iPods. I don't know, you probably don't even know iPods anymore, but these were devices where you choose songs, and the random, the shuffling of these songs actually was not possible to achieve randomness with the shuffling, because in randomness you actually have repetition of songs one after another, and this repetition you want to avoid. So randomness means that there could be repetitions which on an iPod you don't want to have. So for that very reason, they actually had to implement an algorithm that would avoid repetition. By that, you basically, per definition, you're not using randomness anymore. So it's actually, they labeled this, and you may have seen it on iTunes. Some earlier versions had this note that it's actually, it's less random to make it feel more random. So it's also, there's randomness that we actually observe, and there's the randomness we perceive. So randomness is actually, yeah, no? So the randomness we perceive is the randomness where there's no repetition. But real randomness actually would come with repetitions on the songs. So if you hear your favorite song twice in a row, for you personally, on a shuffle, on an iPod or on iTunes, it wouldn't feel random. But they actually had to alter the algorithm in a way that this would never happen, because by that, it felt more random. So that means that randomness is hard to achieve, and not everything that seems random is really random. That's why the quantification of randomness is actually something you really gotta keep in mind, particularly in research, where this really can trick you and confound your thinking. It's just as an example to emphasize how important randomness is, how tricky it is, and how important that is what we're gonna discuss today. So we will be talking about sampling and probability. So why is that important? Because samples will allow for you to understand populations. We talked about samples and populations. You cannot study an entire population. You can do a census, you can create registries, you will understand populations to some extent. But if you really want to study populations and understand dynamics in populations, you need to create small samples. And these samples should represent the entire population. And for that, you need some randomness to essentially provide each member of the population equal chance to be selected in your sample. Why do we need that? We need that because we want to have a sample that is exactly representing that population, which is something that is called external validity or generalizability. So just assume any study that you will conduct. Every study, essentially you want to have a study where the results are equally applicable to everybody in the population. For that very reason, the dynamic you see in your sample needs to be consistent with the dynamic in the population. We'll talk about this in a little bit. So preferably, every sample you're drawing is a random sample. It is not always. And here you have listed the so-called convenient sample. So a convenient sample is a sample that essentially is a sample that is easily available. Why would you choose such a sample? Any ideas? Yeah. Yeah. Yes, so that would be a specified kind of subselection, so to say. So that's subsampling. Goes in one direction, yes. Would be one reason, but the convenient sample per se implies already to some extent why you would choose it, because it's convenient. So when you, for example, when you want to study, let's say you want to make a survey in the New York City population, and you want to sample a part of the population that is representative for the overall population, And in that survey, you ask random people on the street for their preferences in terms of, I don't know, their shopping behavior. And you do your convenience sample right next to your apartment, and that's, let's say it's close to Bloomingdale's, is not representative to an overall sample because there's a certain fraction that may go to Bloomingdale's as an example, right? So there's some form of convenience included. Or there's college students that you would sample because you're studying psychology in a college and you only ask colleagues that you meet on campus. That's a certain kind of what we call in research and epidemiology selection bias. So you select a group of the population that is not representative of the overall population. Selection bias caused by a convenience sample because it's convenient for you to access this population. Matter of fact, and that's nothing for the quiz, matter of fact that a majority of all randomized controlled trials, and this is the form of trial that you would use to basically establish some really solid evidence for the prescription of antihypertensive medication or every form of medication. The highest level of evidence is a randomized controlled trial, only topped by an aggregation of several randomized controlled trials, which is meta-analysis. We'll talk about this later. So the problem with that is that the majority of recipients of such treatments are patients that are in the Medicare kind of elderly population. The problem is the studies are conducted in people that are they're much younger, they're more likely to be male, they're more likely to be college educated. So they're differing from the overall Medicare population. And there are studies that actually studied the study participants and compared them to the Medicare population. And they actually have found that there's a substantial difference between these two groups of people. So the population is entirely different than the sample that you have used for your RCTs. And that's a well-known, well-established fact. But you're doing this based on the premises that you think it still will have the desired effect, and it will still be as effective. But it's a huge ongoing debate. And this is also why meta-analysis is so important, because by replication, you establish that the dynamic that you have observed in your sample is still sufficiently representative for your population. A convenience sample is one of the biggest problems, a big problem you have in clinical research. Any questions to that? It's a pretty interesting topic, right? It's kind of inspiring when you think about it, because it's something you would not commonly think about. So it's very important to keep in mind. Okay, random sampling. Every member of the population has an equal chance of being selected. They're almost never used in social sciences because it's pretty hard to do that. And it's difficult to access the whole population, which to select the sample. The convenience sample. So that's a sample that uses participants who are readily available. Talked about it. Why would you use convenience sample? For the sake of having a more convenient sample. Convenience sample does not represent the larger population, and it differs in terms of generalizability. And this is what we have discussed before. Generalizability is this external validity that you can say, my sample is exactly like the population. My dynamic in the sample that I've observed is exactly the dynamic I will observe in the population. You likely cannot often say that. It can be improved with replication. I alluded to that. So you basically do randomized controlled trials. You don't only do one, you do 10, and you put that together. You use some really fancy statistical models, and you get an overall estimate for all your 10 randomized controlled trials. And by that, you can basically sufficiently reliably say that this essentially is really a dynamic you will also see in your population. If there are differences between the randomized controlled trials and in the samples that were collected, you can establish quite reliably that this dynamic will also be seen in the population. What is even worse than a convenience sample is a volunteer sample, because a volunteer sample comes even with a greater risk of selection bias, because in a volunteer sample, You have somebody raising their hands and like, yeah, I want to do this trial for whatever reason. Makes it even worse. And this is true with crowdsourcing. So where you basically say, so crowdsourcing essentially is something that becomes more and more popular. So we have crowdsourcing and crowdfunding. I don't know whether you heard of crowdfunding. That's like Kickstarter, where they're like, okay, so who wants to sponsor my invention? I want to go into production. Then you have crowdsourcing, where you kind of try to find within the overall population is like, who's going to help me do this and who's going to fill out my survey? You find those things. The problem with that is there's a reason why the individual went on that website. There's a reason why that individual chose to participate in that research. That reason may bias, not confound, bias your outcomes. Even worse so when you do online network sampling like MTurk. I don't know, does anybody know MTurk? That's the Amazon Mechanical Turk. That's basically an Amazon, it's part of the Amazon commercial empire. So essentially you can create an account with Mechanical Turk and you can do random small jobs, digital jobs, like, I don't know, it's not really as simple as like doing an Excel spreadsheet, but hypothetically that's what it was meant, is like somebody has an Excel problem or has a digital problem, and somebody offers and solicits their services and they match together and yeah, you do something for that individual. So it's usually like data entry, stuff like that. But mainly it's surveys. So you can go on Mechanical Turk, fill out surveys, and you get like a marginal amount of money for that. It's yeah, it's really a small and negligible amount of money, but it's money. So you can earn money by filling out surveys. As you can imagine, convenience sample or a really biased sample. Particularly since you're receiving money for that, you will more likely give results the person who's designed the survey will want to hear. If it's, for example, a product sample and you're receiving money for filling out that product survey, or you have the chance to win a prize, it's known in the marketing world, it's well known that these surveys are totally biased. So as soon as somebody has somewhat a prospect of gaining something from it, they will basically beautify their input, and it's not going to be a reliable input. So this is the online network sampling. So any questions about convenience samples, volunteer samples, generalizability? Yes. Once again, please.
How would you get a sample if you don't have volunteers? You can just grab a population sample, a population example.
Yeah, that's a very good point. So the question is, how can you actually manage that if you don't have a volunteer? So that's a very good point, essentially. You likely will not, because the willingness to participate by itself already creates a selection bias in a way, right? And that's what I meant before, is like the RCTs are essentially all biased compared to the Medicare population, because if you have an antihypertensive medication, yeah, it's like a 95-year-old will not participate in research that essentially comes with a certain risk, particularly in a group with a comorbidity. So it's likely going to be somebody who's younger. Somebody who's younger is also more interested in research. Then you have those with college degree, which is also known, they're more likely to have college degrees. It's because they're just more interested in research, right? If somebody doesn't really have the cognitive level to be interested in research, they may not be as interested in research. That may be not true, and that may be something I shouldn't have said at this point, but yes, there's a probability that somebody with a certain educational level may be more interested in research. So there's a selection bias that comes with that. Absolutely, 100% right. In the epidemiological world, it's a little easier because you get de-identified data. So you can, to some extent, it's also in my world, and the epidemiological world is a problem, but it's easier because you get a priori everybody in your population. So there's a little bit more randomness involved. Okay, I'm saying it, randomness. But yeah, so it's definitely a problem. So so to essentially the willingness to participate creates a selection bias, and you're absolutely right. So yeah, so it's difficult on all ends. Clinical research suffers from a lot of limitations. That's definitely one of them. But really good question, an important question. Any other questions? Yes. Yeah, that's replication. Replication is one of the ways how you can circumvent the problem by basically replicating it in different sample populations, and finding similar dynamics will allow for you to understand dynamics that are generally applicable to a population. Then there are some statistical methods how you can evaluate what hypothetically could change, and then you would go into subsampling. So once you understand that a certain population, and it's, let's say you have an effective drug, and then you have a group of patients that are not showing the effect that you are anticipating, then you would kind of study that subgroup to understand why they do not have this effect. So this is where you basically you would subsample it. So you would take a subsample that kind of is of specific interest. Then that's one way to deal with that. Statistically is another way to deal with that. And also when you have in randomized controlled trials, you essentially you have, if there's a subpopulation, it's not as effective, you balance it between both groups. So you don't take the selection bias out of the equation, but you balance each characteristic between both groups. So when you compare two groups. So, but selection bias is hard to circumvent. It's really difficult. Adjustment is one way to do that. But yeah, we will hear very late in the course what adjustment is, but there are statistical ways to take this out of the equation, at least to some extent. Any other questions? All right. So this, I alluded to that before briefly, product reviews, product surveys. You essentially have no evidence that a testimonial is essentially really reflecting the quality of a product. So when you talk about a nail polish at Sephora and you read the testimonial of that nail polish, matter of fact is there's a reason why that person, well, it's most likely a woman, why this this customer has chosen to write a testimonial. That's by its own right. It's already biased to the fullest. So it's really very complicated how to essentially find surveys and survey insights that are unbiased. So random assignment. Okay, so now we're coming in the world of randomized controlled trials. So to explain that. So when you are studying, and we have briefly talked already about that, about an intervention where you basically allow for an individual to be part of a fitness program. And you want to improve, let's say, blood pressures, fitness, athletic performance. So you basically you take that fitness program and you take a population, let's say a school class, and you assign one half of the school class to be part of the fitness program, and you assign the other half of the class to not receive this intervention. So now when you study both groups without randomization, you have a possibility that you will have more individuals that do already regularly exercise in the group that is not part of the fitness program. So essentially what happens is your effect on the group that is assigned to be part of the fitness program will not be as strong as compared to that group already that already has a higher level of fitness. So you're quote unquote diluting your treatment effect of the intervention. So you're not helping your case to make it easier for you to see a difference between both groups. So for that very reason, you want to randomize between both groups that you have a comparable fraction of active people in each group. By that, you keep it balanced between both groups, and the intervention that you're employing at study day 0 up until the end of, I don't know, 6 months, will essentially be really reflecting the dynamic in a population that you meant to sample from. That's why random selection is important, to keep it balanced. Yes?
Does it only have to be with 2 groups, or
it can be more. It can be as many groups as you want. The problem is with the groups, you just got to keep in mind that each group needs to have a certain size to be reasonably powered to essentially give you a result and a difference that really is meaningful. But good question. Any other question? Yeah. So random selection. You mean random selection and random assignment. So random selection would be, and this comes back to your question from before, does a volunteer to a study not already represent a bias? And it does, because random selection would be that you randomly select from a population and you take each individual out of that to essentially participate in your study. As you can imagine, with clinical research, this is not really doable, right? Where you can, well, there are some rare cases where you could do it, but it's there's an ethical commission, the so-called institutional review board, that would review every study that you're conducting. It would need to be quite an interesting and well-designed study to do that. We, for example, we had one where you could have done it, which was sampling of COVID-19 from face masks of patients that come in dialysis clinics. So that was exempt from consent. So patients didn't have to consent, but only under the precondition that we would not identify those patients. So we would only take the face mask, we would put them in Ziploc, and then we would test them in order to see, as a proof of principle, whether it's possible to sample COVID-19, the virus, from a face mask. But without identification only, because if you identify, then it already becomes prospective clinical research. So this is where it's getting tricky. So random selection is really very hard to kind of find. Random assignment, random selection would also, you would mean to assign each individual then to a certain group, right? So you take somebody who is who would then be randomly assigned to receive a fitness program, and so it becomes kind of tricky. But random assignment is easier because you have a pool of willing subjects, and you assign them to each group, and by that you essentially get them balanced. So this is what's meant here. Yes. Any other questions? All right. So random selection is almost never used, but random assignment is frequently used. Equal chance of participation. And now we're coming in the realm of probabilities. So probability is central to inferential statistics because conclusions about a population are based on data collected from a sample rather than on anecdotes and testimonials. So what does that mean? So what we're trying to do, we're trying to understand dynamics in populations based on dynamics in samples. That means that one of the outcomes is always probability. And you will hear about that when we're testing differences between two samples. You will hear about that when we test differences of a sample from a population. You are testing hypotheses that essentially are then accepted or rejected based on the so-called probability value of this finding, of this difference that you're seeing being seen because of chance or because of a real difference. That's when we need probabilities already. And what does that mean? Whether this is indeed a difference rather than anecdote or testimonial. Inferential statistics means that you're trying to see dynamics that you essentially solidly can believe and that you solidly have tested for the probability of just being a random finding. And anecdotal evidence in that context is where you hear anecdotes about whenever I take this medication, I don't feel well. That, for example, would be one of those anecdotes that you hear. Or I don't know, whenever Aunt Frida takes this medication, she doesn't feel well, right? These are anecdotes that essentially don't really represent statistics in a way that is generalizable to a greater population, because it's only the anecdote of one observation or 5 observations as such. It doesn't really represent the dynamic in a greater picture. And from that end, yeah, anecdotes and testimonials are biased, and they're essentially not the probability that you really solidly can believe. And this comes back to perceived probabilities and actual probabilities. And this is where randomness is sometimes different than the perceived. So it's different between perceived randomness and actual randomness. And this comes back to the iPod example from before. And anecdotes and testimonials are biased, as we have talked about. That's particularly obvious in the personal biases that are stated down there. A confirmation bias essentially is something where somebody has a belief that he or she finds them confirmed by whatever observation that is being seen. There's a confirmatory bias. And you have illusionary correlations, which is, I like that example, and this is actually the Nolan Heinzen book. I only win that race, race whenever I wear my talisman. So it's something where people build their own beliefs, and by that find it then confirmed or kind of believe in it so strongly that you almost may have a placebo effect already. So it's correlations that are not really correlations, that is basically just something that's on a personal level and something people embrace. Yes. Goes in that direction, yes. Goes in that direction, yeah. But it's interesting, it's like, yeah, sometimes you know that. Okay, probability part 2. Any other questions? Probabilities. So now it's getting a little bit more in the realm of real probabilities. So probability essentially is the likelihood that a particular outcome out of all possible outcomes will occur. So we have the personal probability again. That's the subjective probability. So I foresee a 40 to 50% probability I will have dinner tonight after I return home from class. That's a personal probability. Where for myself, I'm making up a probability, and I'm stating this or nothing. It's just a good friend of mine, actually. So he's he has a saying, he says like 99% of all statistics are made up on the spot. It goes in that direction. What's the value of these probabilities? Quantitatively, not much. Qualitatively, maybe a bit. because if you're less than 50%, so I had dinner already, so I may not have a second dinner later on coming home. So yeah, it's less than 50%. So qualitatively, it makes it less likely I'm going to have a second dinner, but quantitatively, no, there's no probability. So the metric is kind of useless. Where probability is getting more important and more interesting is when it comes to expected relative frequency probability. So what does that mean? You have a trial, which is an attempt, rolling a dice, rolling a die is, for example, one trial. Then you have an outcome, which is, let's say you want to roll a 6, the outcome is the 6. Success is I rolled the 6. So what's the probability of rolling a 6? 1 out of 6. 1 divided by 6. That's like, what is that? Like 16%, somewhere there, right? 16.6. So when you roll a die 100 times, how often is 6 gonna come? Based on the probability that you have just stated, what would you think? 1 out of 6 multiplied by 100, right? So if you do it 1,000 times, again, so it's essentially when you have a probability of 1 over 6, and that translates into 16% of probability. If you do it 10,000 times or 100,000 times, you get 16% of whatever number. Why is that important? It's important because I carry you back into my world of epidemiology. Okay, so you're sitting in a doctor's clinic. You're the doctor. And you're trying to estimate the probability of this individual that just entered, that patient that just came in to have diabetes. Let's say the prevalence of diabetes in the population is 10%. That's kind of arbitrary number. 10%. What's the probability of this individual having diabetes? 10%. So you have 100,000 patients coming in a clinic. How many diabetics are you going to have? 10,000. So this is important to understand because the probability propagates them. And when you look at an overall population, that probability you have on one individual is the same probability you have in 100,000 individuals. What modulates and what changes this probability is then the characteristics of the sample. So if you have, let's say, the general population, and the general population probability is 10%, and what we refer to in epidemiology as the so-called prevalence, and the prevalence is essentially also translating into the probability of randomly picking a diabetic out of the population, is then different in different samples. You take a sample of individuals that weigh, let's say, okay, so you have a subpopulation of overweight individuals that have an extreme body mass index of greater than 35 kilograms per square meter. You will, and this is well established, have a greater probability of finding a diabetic. So the prevalence is different. Consequently, the probability of you randomly picking a diabetic is going to be higher. So that's what that means. So this is trial outcome of success. Is essentially you try to pick one. The outcome is what you predefined, which is diabetic, yes, no. Success is you actually pick the diabetic. Law of large numbers means like if you are having large numbers of which you sample, so you take a lot of trials and you pick like 100,000 individuals from a population of 1 million, you essentially will in these 100,000 people, the probability and the number of individuals that they pick with your outcome will essentially be consistent. It will be the same number. That's the law of large numbers. The larger the number of the trials, the more likely the probability will translate in perception of the percentage of individuals in your population. The problem with probabilities is that all your draws need to be independent from each other. And they need to be independent of features of characteristics, because the characteristics of your sample will affect your probabilities. And this is important, particularly for data exercises that we do. Any questions on that? It's pretty interesting, right? This is really what goes in the realm of epidemiology. So calculating probability, we just talked about it. So you basically determine the number of trials. So you know that you will have, you roll the die 10 times. You have success, which is rolling a 6. And the probability is 1/6 multiplied by 10. It's the number of trials, it's the successes, how many successes you have. Let's say you do it 100 times, you have 16 sixes, and you did it 100 times, so it's 16 divided by 6. Is 1/6, the same probability. It's easy in that context. The confidence is the personal probability and the rating of our confidence that this event will occur. This will become important later when we talk about the confidence interval. The confidence interval essentially is, no, let's not go there. No, but it's a probability that you can determine or predict something, and this is a reflection of your own confidence to do that. It's usually depending on the number of trials you have seen and how realistic that estimate is in your own perception. We will talk about that more once we get there. So in inferential statistics, and this is basically, so we have talked now about central tendency and variability. We have talked about describing populations. We have talked about samples. We have talked about histograms. We have talked about how to see frequency distributions. We've talked about these things, which essentially are in the realm of descriptive statistics. So now we're moving from descriptive statistics slowly in the realm of inferential statistics. And the inferential statistics is basically where you develop a hypothesis and you use probabilities to test these hypotheses. And I talked about it before, it's like that probability is going to haunt you because we're going to use, we're going to develop hypotheses. We're going to develop hypotheses relating to differences between sample populations or samples from populations. And you will use the rules of probability to essentially test these hypotheses. And this is really a lot of fun. So you will use these probabilities to actually make decisions on whether you reject or you accept the hypothesis, the null hypothesis. And this is where we're going now. So now hypotheses are basically stratified in two. So you have a so-called null hypothesis, and you have a researcher alternative hypothesis. A null hypothesis is where your hypothesis is not true, so there's no difference. This is your default hypothesis. You always assume that there's no difference. This is how you will start off. You're rejecting your null hypothesis. Your null hypothesis says like that if you take the overweight group and you compare it to the normal population, there will be no difference in the probability of picking a diabetic. That's your null hypothesis. And now you're building the probabilities to an extent that you will reject this hypothesis. And we'll talk about this a little more. But the null hypothesis where you start off, you're basically saying that I hypothesize in my null hypothesis that there's no difference. And then you're trying to reject and find a probability that this is essentially not the case. And we will learn how to do that. In terms of terminology for randomized settings, randomized studies, you have two groups. And we talked about an intervention, right? We talked about that fitness program. That fitness program is an intervention that the control group will not get because it's a randomized controlled trial. And controlled stands for like, there's a control group which does not get my intervention. And therefore, this intervention will only have an effect in the experimental group. And now I'm following both groups, control group and the experimental group. And I will, at the end of the day or at the end of my study, I will see effect only in the experimental group. And I compare it to whatever is seen in the control group. And the difference between both groups in terms of activeness, athletic performance, blood pressure, whatsoever, between those two groups, that's my quote unquote treatment or intervention treatment effect. That is the outcome of your randomized control trial. And this is why it's important to randomize between both groups, because you don't want to have confounders in there. You don't want to have, I don't know, a preponderance of hypertensive individuals in your blood pressure control group that would dilute your effects. You don't want to have, I don't know, super fit, active, exercising individuals in your control group, will dilute your effect. So you want to balance those between both groups. And this is what this means. Yes. Well, in the simplest setting, it's basically you have a clinical research coordinator recruit an individual, and that research coordinator goes down to an Excel spreadsheet where you have like, okay, so this was individual number 5, and so there's a random grid that you can do in Excel or in any other program where you basically do like so you basically you know your outcome, you know that you have 50 individuals, and Excel will create for you a random kind of 0 or 1 balance. So it will create random algorithms to kind of do the assignment for you, which is going to be randomized. So you have 1 is going to be in that group, 2 is going to be in that group, 3 is going to be in that group, and then you have people approaching, enrolling and recruiting participants. And that becomes then research subject number 5. And then you go and you check, and then you basically see, okay, control group. And you assign that individual formally and officially the number 5 and becomes a member of your control group. Yeah, but that's exactly the point, because you don't know it, but you automatically predefine your randomization before you even start recruiting. And just by the fact that you randomly assign them to either of these groups, automatically you will balance them as a consequence of the randomization. Does that make sense? Yeah. And so you also got to see it that it needs to be so it's a 50-50 probability at this point. And when you have a larger group and a larger population that you're recruiting, then it becomes easier to see that. But it's like, again, perceived randomness and actual real randomness. But good question, important question. Any other questions? So we talked about it already briefly. We talked about hypothesis. So there's a null hypothesis that essentially is where we have no difference. If you reject the null hypothesis and you accept the research or alternative hypothesis, you actually found a difference. If you fail to reject the null hypothesis, and we will learn about what that means in next class, actually, no, in 2 classes. You conclude that it did not find a difference. So this is a failing to reject the null hypothesis and accepting the null hypothesis. So you need to think a little bit counterintuitive at first. It becomes more intuitive once we actually talk about hypothesis testing. But it's important that we have a null hypothesis where we have no difference. Then we have an alternative hypothesis where we have a difference. And essentially what we're testing is whether we're rejecting the null hypothesis or not. This is the test. Yes. It's essentially, it's two hypotheses. It's a null and a research hypothesis. So null hypothesis, no difference. Research hypothesis, a difference. Testing is, we're testing against the null hypothesis. We're rejecting it at the probability that this is due to random chance is smaller than 5%. And this is essentially, this is the definition of rejecting the null hypothesis, accepting the alternative hypothesis. You actually, as a researcher, you want to reject the null hypothesis, because if I say, okay, I did this randomized control trial, I spent like millions of NIH dollars to essentially conduct a multi-center trial in the US, and I'm testing my antihypertensive medication, which is totally novel and totally groundbreakingly new. You essentially want to see it at the end of the day, you want to see a difference between your control group and your experimental group, right? That's this difference, because you want to reject the null hypothesis where you assume there's no difference between both groups, but you want to reject it. And this is actually what leads us to, okay, we're coming later to that. This is essentially where we're coming to the problem with that, because there are problems with that, with this p-value. In its simplest form, there's no problem, it's black and white, but as we all know, things are seldom only black and white. So, but in its purest form, it would be black and white. Probability that we see a difference because of random chance, smaller than 5%, we're rejecting the null hypothesis. We're happy, we're going home, writing the paper, publishing it, and that's it. It's not always like that, because in many cases, you fail to reject the null hypothesis, but your insights are still important. Or in other cases, you see a difference, you find a significant p-value, and you find this p-value that is smaller than 5% is probability value. And it's meaningless because the difference is so small. So there are many things to consider when it comes to those things. Okay, but essentially null hypothesis, research hypothesis, rejecting the null hypothesis and accepting the alternative hypothesis if you rejected it. And okay, this is again the same thing. So null hypothesis, no change or difference. You fail to reject the null hypothesis. Research hypothesis, this one is not supported. Research hypothesis, you see a change or a difference and you reject the null hypothesis. Good. So now there are problems with that, as I mentioned. Problem number one is you're committing a type 1 error. The type 1 error is when you are rejecting a null hypothesis that essentially is true. So you conclude there's a difference, but there's actually none, which is a problem. Essentially that happens when you create subsets that you shouldn't have studied. Or when you have, for example, when you have disbalance in groups, when you have more diabetics in your group, but you shouldn't have studied them in that fashion. If you have disbalancing groups, this could happen. If you subset groups, if you do smaller subset, and you're subsetting to an extent where suddenly you see a difference, and this is done, it happens, then you would commit a type 1 error. A type 2 error is also a problem, because this is when you fail to reject the null hypothesis, although you should have rejected it, which is also a problem. Also happens quite frequently. Problem is usually that the sample size was not large enough. So investigators didn't study enough subjects. So, but it's important to keep these two in mind. So type 1 error and type 2 error, they're both problematic, and they're both pretty big problems in research. Yes.
Also had this question in psychology class. Hypothesis, but I was there will be an effect. But if I do an experiment to see like the effect of certain drug on depression or whatever, I have an assumption, like that if it will be negative or positive. Like I don't just say I want to see if it affects or not. I also have I do my hypothesis like it will be like a negative effect or positive effect.
Yes.
So what if I like my hypothesis would be like the more people take, I don't know, Advil, the more depressed they will be.
Yeah.
And then I found out exactly the opposite. Then it's like rejecting both hypotheses.
And that may very well happen. That can happen, yes. So it goes in both directions, right? So you can have hypotheses that go in both directions. So, but the null hypothesis will always be that there's no difference. So you can directionally hypothesize. So you can have one-tailed, one-directed or one-sided hypothesis, but that's very advanced already. So at this point, you will need to change the probability thresholds for doing that. So this is something we will discuss in a couple of classes from now. Yeah.
And I write my hypothesis. Should it only say if there will be, like whether there will be a connection between X and Y, or should I also include in the hypothesis?
You can do both. I'm a reviewer I have reviewed for good 20 journals over the course of my work history now, about a short one. But I would say I have seen one paper that basically used a directed hypothesis. So it's not very common to do that. This is the difference between a one-sided and a two-sided hypothesis. You would usually not use one-sided hypothesis because it allows for you to use different thresholds for the so-called p-value that renders an analysis significant or non-significant. And for that very reason, it's usually all alternative hypotheses would be stated as a two-sided test. I know that it's right now hard to explain. Let's put it that way. If you're only directing it in one direction,
the amount of light on the ski or whatever.
yes.
I think I know what will be, like I have a guess, but
yes.
I don't direct it.
Yeah, but if you don't direct it, you have a two-sided test. Then you're sticking with your 5% probability value. So it makes, conceptually, I know what you're saying, and I understand what you're saying. It's just like taking an antihypertensive medication is like, and it lowered the blood pressure, right? What else is gonna do, right? That's what it's designed for. And I know where you're going with this. The problem is on an arithmetic statistical level, you would still do a two-sided test where hypothetically this can go in both directions, and you're just comparing it to no change. So statistically, that would be the most commonly reported form of testing. And we will talk about that with the hypothesis testing, where exactly that becomes a very prominent question. Because if you do a one-sided testing and you're assuming a direction, this changes the statistical procedure for you to determine the critical value and to determine whether there's a significant difference or not. So on statistical grounds, it's most common to basically use two-sided testing. But it's a very good question, and I agree that in many cases it makes a lot of sense because it just doesn't make any sense. It increases while it should be decreasing. I agree, but it's in statistics, it's more conservative. Because if you assume a one-sided test, it makes it somewhat more likely that you will sense a difference because your critical threshold is smaller and your p-value changes. But we'll talk about it once we get to hypothesis testing, but it's a very good question. It's an important question. But you're right, in principle, yes. In many cases, it would make sense probably because it's unlikely that it wouldn't go in a predefined direction that you can anticipate. You're right. But again, in principle, let's stick with that for now. But does it to some extent address your question? I hope so. It becomes more complex if I would explain in more detail, but it's like it's yeah. I will remember and I will refer to it when we talk about this. Yes, another question. All right. So again, type 1 errors, type 2 errors, type 1 errors, we see a difference we shouldn't have seen. Type 2 error, we do not see a difference that we should have seen. Both problematics, both big issues in research. And this is what I meant before. The shocking prevalence of type 1 errors. The problem is we all want to see differences, right? I want to test blood pressure medication that is effective. I want to test fitness programs that are effective. It's more likely that results that do essentially produce significant differences, where we actually see a difference that we should have seen, are being reported. The problem is, again, you assume a difference, but the difference may not be there, although you would have liked to see it. That you essentially will, with subsetting, you can produce type 1 errors. These type 1 errors will be reported because they're significant results. The problem is some of these may be type 1 errors, and then in meta-analysis, you see only that one study of that one investigator that essentially was pointing in that direction, or the other studies pointed in the other direction. So that's indicative of the possibility of a type 1 error. Doesn't mean it's 1 for 100%, but it could be one. So the problem with that is now that this happens because negative results that do not show a difference are likely to not be reported. For that very reason, because who's interested in a negative result? Well, the community is, because it may be that an investigator has just published something because it was significant only. So you may be looking at type 1 error, but then you have 20 other study groups that have not seen a difference, and you're disregarding their results. You're just taking this one guy who studied like 10 patients and like saw a significant result. It's like, yay. But 20 other studies that studied like hundreds of patients are never been shown. So now in the community, there are now journals out there that basically focused and exclusively invite researchers to submit negative study results. Because negative study results in many journals will be rejected because they've been negative and they don't receive that attention the journal wants for themselves as a journal or for that investigator, for that article. So this journal for negative results essentially allows to create a forum for studies that have negative results to be published. And then they go into meta-analysis, and then they actually become a piece of evidence informing the community. So that's the idea behind it. And yeah, the shocking prevalence of type 1 errors. That's the explanation. Any questions on that? All right, because that brings me to the end already. It's not been as short as I thought it would be. We're actually quite on time. So are there any questions on anything R related? Do we want to speak about the practice lab? Homework? Okay. What is the question on the homework? Oh, you want to show me something? Okay, but I will do it after 7:20. But yeah, so you want to speak about the examples in the homework? Would that be helpful?
Yeah, I guess that's the question. For the second question, what would the X be if there's age and gender? Like which one's the X?
So let's look at the question briefly.
Yeah, like the X variable, is it age or time?
So let's look at the second question. So you're talking about this scatter plot, right?
No. I was actually talking about the standard deviation.
The standard deviation.
Like when you're like the first step to find the sum of X, what would I'm just confused which one X would be if I should add the age or I should add the time.
I'm kind of not following, sorry.
When you're finding standard deviation, like the long way,
Yes.
the first thing you have to do is find the sum of X, right?
Yes.
So for this problem, should I add the time, like all the times from the term, or should I add the age?
So we have ranges of time, right? This defines the groups.
Yeah.
So you have here entries where each of them has an entry in a group. So the way I would start this off would be to do a frequency table, right?
Yeah.
And each individual here has a spot in each of those ranges. And that range essentially will then, each entry will produce one age. So you have in each group, if you do the group of 40, you only have 2 entries, which are 65 and 62, right? So now, what's the average? So what is the outcome?
I don't know, I'm confused which one to look at, the age or the time.
So you create a group frequency table within ranges of time. You have 40 to 49, 50 to 59, 60 to 69. Proportion of employee in each group, percentage of employees in each group. Use the age entries in the group to calculate the mean age and the standard deviation of the age for each group. And I don't mean to be annoying with these things, but I know, no, I'm not, but it's important to read the question super carefully. And this will, and this is only, this is an example that I made up, right? Which is maybe not the best example. I'm not debating this even. But the point is, like, it's important to read very carefully. Because the practice quizzes, they will sequentially and now progressing into the semester, they will get trickier and trickier. So, and just like reading is really most important thing. As an anecdote from my own life, So when I studied back in Austria, I had all my exams verbally. So essentially meant like I had exams that lasted an hour and a half, and you basically had a conversation with the professor, and they would like, which wasn't always nice because of like they also were not all nice, but essentially you had like a verbal exam. The first thing I needed to learn when I came here, I needed to learn how to learn for a written exam, which was terrible. It was really not fun. So it's like reading the question is really half the bill. It's like, it's tricky, and it's important to keep in mind. Okay, but okay, enough about that. Okay, so it's age, and the standard deviation is then basically each entry minus the average. If there's only one entry, there's no standard deviation. Interesting. Okay, what else? Then we have develop a scatter plot to see whether there's a relationship between time needed. This is when you don't use the groups, not the groups, the actual entry. You're using the continuous variable. You remember continuous variable and categorized variable. This becomes, these ranges, what form of variable is that? It's pretty much a nominal variable. It's kind of ordinal because it has a ranked order, but I would say it's nominal. It's actually more ordinal. So, and then looking at the relationship. So the relationship question was something we did in the earliest classes. So where you want to see in the scatter plot, you want to see trends over time. Right? Preferably you do it in Excel. I think we did the athletic performance in Excel, right? We did that scatter plot with a trend line. I think that should be fun. Yes, we did in lab 2. Yeah, if you, this is how you really get brownie points if you do it in R. That would be the nicest thing. The homework in R, that would be a dream come true. Okay, so 7:22. I think we can conclude for today. Thanks for staying 2 hours longer. Hope the concept was interesting. I'm really sampling and probability is actually a class I really like. So that's really that's